In the previous lecture, we created what's called the field tensor. So we now have a field tensor F mu nu, and we also have a dual tensor, which we call G mu nu. Okay, and with those now, we can write down Maxwell's equations. So prepare yourselves. Maxwell's equations now in tensor notation are the derivative of F mu nu is equal to the current density, and the derivative of the dual tensor is equal to 0. So now we have reduced the 4 Maxwell's equations into 2 Maxwell's equations. So I'll write down the old way we used to write it. So the old notation was this right here. So those are our original Maxwell's equations, and in that form, but this form with just 2 equations right here is actually what would fit into special relativity. So starting with Maxwell's old 4 equations, we actually want to write them in a form which conforms to special relativity. And that's essentially what happened since Maxwell wrote them down until Einstein came along. Next, let me prove to you that writing Maxwell's equations in the tensor formalism actually will give us the 4 equations that we're used to writing down in the what I keep calling the Gibbs notation, with the del's and the cross products and the curls. Okay, so let's start with the first Maxwell equation, and that is this derivative of F mu nu over nu is equal to mu 0 j. So if you notice that this derivative has raised indices in nu, which really I like to write as this to show that it is the dot product, or essentially the divergence. So what I'm saying is the divergence of the field tensor with respect to nu is now gives us a current, a 4-vector j. So let's just take a look at one of them. So let mu equal 0. So what we have is an equation that looks like this. And when I write out this divergence or dot product as 0, 0, x0 plus f0, 1, x1 plus derivative 0, 2 over x2 plus the derivative of f03 over x3. And now if I write that out, then what I get is 1 over c. f00 is 0. So I'm taking the derivative of a 0 plus 1 over c dx. Yeah, so d ex dx plus 1 over c I plus 1 over c, basically the derivative of all the components, like so. So this is 0, that disappears, and what I'm left with now is 1 over c, basically the divergence of the electric field, just the spatial components of it. Okay, on the right-hand side, I have mu 0 j0, which is mu 0, times the C times the charge density. So C times the charge density. So when I put them all together, I get 1 over C divergence of E is equal to mu 0 C rho. Divergence of E is equal to mu 0 C squared rho, which is mu 0 1 over mu 0 epsilon naught times rho. The mu 0's cancel. And what I get is Maxwell's, first equation. So just the 0th component of, so setting the index mu equal to 0 gives us Maxwell's first equation. Okay, what happens if we set mu equal to 1? So if I set mu now equal to 1, I can repeat this, and I would get f10 dx0 plus df11 dx1 plus df12 dx2 plus 13 dx3. And all of this is equal to mu 0 j1. Okay, so let me put the components in. I would get 1 over C d minus EX over C dt. So basically we're looking at the second row of the field tensor. And I would get plus d0 dx plus dbz dy minus dby dz. And all of that now is equal to mu 0 times the jx component, because that's what j1 is. Okay, so now we'll kind of clean this up. This is 0, and these two terms together give me the x component of the curl of the magnetic field. So what I'm left with then is minus 1 over c squared, the derivative of Ex with respect to time, plus the curl of B, but just the x component of it, is now equal to mu 0 jx. So if you noticed, mu equal to 1 gives us the x component in every single term. And so what we have in the end is the curl of B, the x component, is equal to mu 0 jx plus 1 over c squared, this derivative of the x component with respect to time. And if you remember that 1 over c squared is equal to mu 0 epsilon naught, then what I get is the curl of B x component is mu 0 j component of the current density plus mu 0 epsilon naught, the x component of the electric field taking the time derivative. So in the end, if you were to look through this, what you would get is mu 0 set equal to 0 gives us Maxwell's first equation. Mu equal to 1, 2, and 3 are going to give us Maxwell's fourth equation. So all of the components of Maxwell's fourth equation. So those four components give us two of Maxwell's equations. like so. Okay. Okay, so what else do we have? Well, we can take a look at the dual tensor. And the dual tensor we said was this equation right here. So now if I was to take mu equal to 0, then I would get g0, 0, x0 plus g0, 1 dx1 plus derivative of g0, 2 x2 plus the derivative 3 is equal to 0. So basically the first row in that tensor. And so what we would get is 1 over c, the derivative of 0 with respect to time, plus derivative of the x component of the magnetic field with respect to x, y, and z. So essentially what we have is the divergence of B is equal to 0. So we get Maxwell's second equation out of that. And last but not least, if we set mu equal to 1, then what we would get is this equation, which is minus 1 over c, derivative of the x component with respect to time, plus 0, minus 1 over c, the spatial derivatives of the electric field, equal to 0. So now if I rewrite this, I can divide both sides by 1 over c, and I would get minus the time derivative of the magnetic field plus the spatial derivatives of the electric field components. This is the curl of E, the x component of that. And so in the end, what I get is the curl of E, x component, is equal to the this would be minus that is equal to the derivative of the x component of the magnetic field with respect to time. And so in the end, what I get is Maxwell's third equation. And so now if you look to the other mu equal 2 would give you the y component, mu equal 3 would give you the z component. So in the end, mu equals 0 gives us Maxwell's second equation, and mu equal 1, 2, and 3 gives us Maxwell's third equation, which is essentially Faraday's law. Okay, so now what we've done is to write down Maxwell's 4 equations. Writing them into tensor notation now gives us Maxwell's 4 equations. So just to summarize, Maxwell's equations now can be written as these 2 equations. So now life is even simpler. If you can remember the field tensor and the dual tensor, you can just write these down, put them in your pocket, and carry them with you everywhere.